Hello and welcome to Fujipoly Putty Webinar February 2019. My name is Tim and I'll be in the background answering any WebEx technical questions. If you experience technical difficulty at any time during this WebEx event, please be sure to submit your technical issue in the Q&A panel and I will assist you. You may also contact our WebEx technical support at 1-866-779-3239. Please note that as an attendee, you are part of a larger audience today. However, due to privacy concerns, the attendee list is not displayed. All attendees will be in a listen-only mode for the duration of today's call, and as a reminder, this call is being recorded. We will be holding a Q&A session at the conclusion of today's presentation. You may ask a question at any time throughout the event by entering it into the QA panel at the lower right of your screen. With that, we invite you to sit back, relax, and enjoy today's presentation. I would now like to introduce your speaker for today, Christian. Christian, you now have the floor.
Hello everybody, and thank you for joining us here at Fujipoly for this webinar today. I'll begin by giving a little bit of background on myself and a brief introduction to the subject of today's webinar. My name is Christian Mainegra, and I have been a sales engineer with Fujipoly for nearly 7 years. I'm a graduate of the New Jersey Institute of Technology with a bachelor's degree in mechanical engineering. Today, we'll be discussing Fujipoly's thermal interface materials. Specifically, we'll be highlighting the advantages of putty-type gap filler pads. So, key topics that we'll be discussing include a Fujipoly product overview, what is a putty versus a standard gap filler, comparing stress-strain curves of putty versus standard gap fillers, advantages of putty over dispensable gap filler, handling and application notes. And we encourage everybody to please submit questions via the comment section. At the end of the presentation, we'll be doing a Q&A session, and we'll try to answer all or most of your questions live. So I'll go ahead and jump right into the presentation. Okay, so Fujipoly is a manufacturer of specialty silicone products. Our product line could be broken down into 3 categories. We have our Sarcon thermal interface materials, which will be the primary subject of today's discussion. We have our Zebra elastomeric connectors and our custom silicone extrusions. So why silicone rubber? There are many advantages to working with silicone rubber. It has good heat resistance, flame retardancy, low compression set, thermal conductivity, electrical conductivity, ease of custom manufacturing, among many others. So what is a thermal interface material? Well, as shown below, even the most highly polished mating surfaces do not make reliable contact surfaces. You have imperfections and micropores, which make complete physical contact difficult. And without that contact, you won't get the best heat path in between your heater and your heat sink. So there are 2 basic TIM applications. You've got a thin film application in which you really don't have any gap in between the 2 surfaces, and what you need is a thermal interface to absorb the air pockets and fill in the micropores between the surfaces to really get that heat moving efficiently. And then you have a gap filler application where you've got surface mounted components on a printed circuit board, and you've got a heat sink or a heat spreader coming down over the top, and so you've got standoffs creating a gap between the lid and the components, and you need a gap filler pad in there to soak up the air and fill in all the voids to get the heat moving out. So Fujipoly's thermal interface material lineup includes gap filler pads, putty type gap fillers, form in place gap fillers, thermal greases, and thin film materials. So our standard gap fillers are we have a good number of gap fillers. We like to offer a wide variety of choices for our customers. Now, some of these come with different options, such as embedded mesh or a reinforcement layer on one side. They range from 1.5 to 6 watt per meter Kelvin, and these are pretty much considered to be general purpose pads. And then we have our high performance gap filler pads, which are typically reserved for high power output and small form factor dies. We have our EGR type, electromagnetic wave absorption type, and this is also a thermally conductive gap filler. And essentially what it does is absorb the energy from electromagnetic waves and converts it into heat and conducts the heat outside into the enclosures. Our silicone form in place material is a thermally conductive silicone gel, which is dispensable, and that ranges from 2 to 5 watt per meter Kelvin. And then we have our rubber type thin film material. So this is a gum rubber type, which is actually extruded into a flat tape. And the other benefit to this is that we could actually create custom profiles and we could compression mold with this material. It's also a very good dielectric material, so it's typically used in power electronics and serves a secondary purpose of creating a dielectric barrier in between the components and their enclosures. And then we have fiberglass reinforced thin films, which are great in situations where you have very high shear, high compression forces, and you really need your fiberglass to maintain the integrity of your dielectric bond, of your dielectric barrier. And now the extremely compressible putty type gap fillers, which is the focus of our presentation today. So we currently have 3 products in our putty category. First is our PG25A general performance material. It is available in thicknesses of 1 millimeters up to 5 millimeters. This is the softest of our 3 putty type materials and is also our largest mover of the 3 putties by volume. It provides a good combination of thermal performance, low cost, and extremely high compressibility. Next is the high performance GRPM, which is available from 1 to 3 millimeters in thickness. And lastly, our highest performance PG80A, which incredibly is available as thin as ½ millimeter and up to 3 millimeters in thickness. And now keep in mind, custom thicknesses are also available for these pads. So our gap filling TIM review. Basically, a gap filler is used to fill in space between solder mounted components and a top mounted heatsink. It's for this reason that compression is a high concern in electronic packaging design. Right, so a thermal mechanical analysis of stresses on solder joints will show the limits to the strains placed on PCBs. Now, an example of how to select the appropriate thickness of gap filler pad. Here we have a scenario in which there's a 1.46 millimeter nominal gap. You've got a mechanical tolerance of plus and minus 140 microns. So your maximum gap is going to be 1.6 and the minimum 1.32. So then when selecting your gap filler thickness, you got to make sure that you're going to have contact at all times. So you'll have to go with a 2 millimeter thick pad, and compression will range from 20 to 34%, which is a good place to be. You would typically recommend trying to stay under 30% if at all possible. Now another example of selecting the thickness, you've got a 1.25 millimeter nominal gap plus minus 0.3. So your maximum gap is 1.55 and your minimum gap is 0.95. So the 2 millimeter thick pad will be compressed between 22 and 53%. So in a situation like that is where a putty type material is really ideal because you have compression ratios above 30%. So knowing your gap is therefore a very important thing. Understanding the variation in your gap is critical to protecting boards and solder joints from excessive strain. Know your gap so you can know the limit on forces exerted during the assembly process and the product life. This will allow for optimal material selection early in the design process. So what is a putty? Our silicone putty sheets are thermally conductive gap filler pads. Putties require a lower compression force to deflect than our standard gap fillers. The difference between a putty and a standard gap filler. So silicone rubber becomes increasingly elastic with the additional reactions caused by catalysts used in the polymerization of the compound. Our putty sheets are manufactured by employing a proprietary cross-linking method that lessens its polymerization relative to that of our standard gap filler material. This enables Fujipoly to create a product which meets the stringent mechanical requirements of our customer base. Analyzing the compression curves of putties and their non-putty counterparts. So here, what we do, we're actually mapping the compression of both putty and their non-putty counterparts at similar levels of thermal conductivity. So they have similar density of fillers inside of them, and we'd like to look at those next to each other, right? So the compression of TIMs is a large concern in the mechanical design process. and sometimes even more so than the thermal performance of the material. This trend is expected to continue as engineers require higher performing TIMs on smaller packages with higher power output. So you can see from the curves that the loads increase as we go up in thermal conductivity. And this is what is particularly challenging to hardware designs when working with higher power components. So the equipment that we use to perform the compression test is shown in this picture here, and what this equipment is capable of is testing a specific size and thickness. We can vary the compression velocity, we can modify relaxation time, and set the equipment to compress the material to a certain percentage of its thickness. So the sample size that we'll be using today is a 1-inch square and a 1-inch square platen, and the compression speed is 5 millimeters per minute. Okay, so now we'll actually get into the compression curves. So we're going to look first at the PG25A and the GR25A. So in each of the following curves, you'll be seeing compression ratios of up to 70% of the original thickness, and then we're allowing 1 minute for the material to relax and recording the drop in load in the duration of that 1 minute. So you can see on the first slide, which is PG25A and GR25A, that in the range of 10 to 30% compression, there's not such a big difference in the load. And now, in a perfect world, this is where you would want to be with a gap filler TIM. You know, above this is where the compression curves begin to diverge from each other, and that's where going with a putty type material really begins to make more sense. The top of the curves will show the highest dynamic load experience, followed by a quick reduction in the stress relaxation period. So static loads may actually decrease by up to 50% of the maximum over time. So now we're going to go ahead and look at the GRPM, GR45A. So you can see, lower in the compression ratio percentage, not a huge difference. They begin to diverge above 40% of its initial thickness. And then here with the GR80A and the PG80A, I have a similar situation. Now you'll notice the GR80A is actually only compressed up to 50%, and the reason being that we have a 2 kilonewton load sensor on our equipment. So as it approached 70%, it actually went above that 2 kilonewton limit. And now, same exact materials, but we'll be looking at 1.5 millimeter thickness. So actually, as you increase in thickness, the difference becomes even more apparent. So this again is the PG25A versus the GR25A, and then the GRPM versus the GR45A. So as we're at 1 millimeter thickness, they were pretty close together until, above 40% here, they actually start to diverge a little bit lower than that, and the GRPM kind of stays low, whereas the GR45A continues to go on an upward trajectory as far as the load goes. This is the GR80A and the PG80A. And now again, finally 2 millimeter thickness is the last thickness that we tested for the purposes of this presentation. So again, you can see the difference between PG25A, GR25A at 2 millimeters, GRPM and GR45A, and finally GR80A and PG80A. And once again, the GR80A exceeded its 2 kilonewton load maximum. Okay, so now we'll look at some of our equipment to actually test for thermal resistance of the material, right? So compression is one of the main concerns, but of course the main purpose of a thermal interface material is to efficiently conduct heat. So our TIM tester is a modified ASTM D5470. It can measure thermal resistance versus displacement. It's got a variable load control, variable displacement control. So essentially what you've got is a load cell with a heater. The specimen is then sandwiched in between the heater and an aluminum cooling unit, with the load cell providing the variable pressure. And then essentially we'll do the calculation, which is a difference in temperature divided by heat flow times the area of the compressed specimen. So we'll look at how to calculate the power density, and then that'll help you decide what kind of material and what level of conductivity you really need to be looking at. So on-chip power densities are critical to selecting the optimal material. So one example is a 38 by 38 millimeter 100 watt chip working at 92% efficiency will dissipate 8 watts of heat. The power density would then be the 8 watts divided by the surface area is equal to 0.55 watts per centimeter square. So this is more than enough for a soft and low-cost gap filler to do the job. The same power dissipation on a 10 by 10 millimeter die surface will give you a power density of 8 watts per centimeter square. Here we would recommend a higher conductivity for the TIM, which also means the material may require more force to compress. Now, the benefits of high-performing TIMs are only apparent at high power densities, but there's actually a little appreciable difference until 5 watts per inch square and beyond. And then you'll note as you get towards 10 watts per inch square, it makes a big difference what conductivity the material that you're using. Now, using thermal resistance to calculate delta T. So here's a table of thermal resistance which you could find on the material data sheets or our SARCON catalogs. And so to measure delta T, you have to take the power density, which we showed in the previous slide, and then the thermal resistance, which you could pull off of the data on the spec sheets of the catalog. So for one example would be an 8 watt per centimeter square power density using a 1 millimeter thick PG80A pad at low pressure. So delta T would be equal to 8 watt per centimeter squared. And then if you look up at the PG80A table, 00-100BL at 100 kilopascals, we report a thermal resistance of 1 degree C centimeter squared per watt. So you multiply the two figures and that'll give you a delta T of 8 degrees Celsius. So this is the temperature drop through the TIM from the bottom of the die from the top of the die to the bottom of the heatsink. And now custom compression and TIM tests are available to our customers. So Fujipoly is happy to provide a TIM test or a compression test for you. We could test thermal resistance versus pressure or thermal resistance versus displacement. We could also do compression load versus deflection using different sample sizes and different plant sizes. Now we'll talk a little bit about the handling of our putty materials. So handling is made easy because the putty is in sheet form. Parts are typically offered kiss cut with the bottom carrier intact. So this will actually eliminate the chances of applying a TIM material with a piece of liner stuck to one side, which would actually increase the thermal resistance by quite a lot. So no special setup or equipment is required to begin using putties. The cost of setting up an assembly process using kiss cut pads is zero or very low, whereas the cost of setting up an assembly process with dispensing equipment can be quite high, depending on the type of equipment and the level of autonomy that you choose. No need to worry about inadequate application of liquids with parts that are cut to size. So kiss cutting. Standard rectangles and squares can be kiss cut using our high-speed XY cutting machines. No hard tooling is involved. And there you see a nice picture of kiss cut squares, so you could clearly see the cut lines in between the material. The material is perfectly separated, one square from the other, but it still remains on an intact bottom carrier. We also do die cut shapes, so they can be provided in kiss cut format by using our presses. Again, you have an intact bottom carrier and an intact top cover film with the material scored onto that bottom carrier. Here's a quick video of our super cutter kiss cutting a sheet of SARCON. The excess materials on the side is just peeled off and discarded. Cut the other direction. And that's all there is to it. And again, just a quick demo on the handling of this material. So typically you would have your kiss cut sheet. You just remove the top cover film, use a putty knife or a spatula or even your fingers to peel the pad off of its carrier. See, it's easily handled. Another quick video of the process. Now these pads also have a high level of inherent tack, which is essential during assembly process because you could actually apply it to the heat sink or your enclosure, and you don't have to worry about the pad sliding around or falling off. It's going to actually use its tack to stay in place quite well. See, it doesn't take much pressure at all to get it to stick to a substrate. So what are some of the existing high volume applications for putty? So putties are used in fiber optic transceivers, set-top boxes, embedded computing, aviation, communication, network equipment, automotive, and military. Fujipoly America Corporation is headquartered in Carteret, New Jersey. From this location, we provide manufacturing expertise, expert technical support, superior quality control, R&D, testing, and customization. And of course, we provide service and we are the service and distribution center for the entire Western Hemisphere. We also have our Customer Engineering Resource Center. This is located in San Jose, California. So San Jose, California has a lot of test capabilities. They could do some of the same things we do in New Jersey, such as compression force and thermal resistance, but they are also capable of doing custom thermal tests, dielectric, viscosity, tension, electrical resistance, heat chamber, thermal cycling chamber, and prototyping capability using our proto cut machine. It's a very nice asset for those located on the western coast of the United States. So just a quick recap. Fujipoly has a wide variety of products to meet our customers' needs. Fujipoly is a market leader in high-end putty type thermal gap fillers. Putties are softer than a standard gap filler without the need to change over to dispensable solutions. Easily handled and requires zero startup costs on the assembly line. Fujipoly excels in quality and customer service. We always aim to provide quick turnaround on sample requests, RFQs, and technical support. Here's some of the contact information for Fujipoly. So out of our headquarters in New Jersey, our customer service manager, Stephanie Minko, our sales manager is James Hopkins, and myself for technical support, Christian Minegra. And then out of our Customer Engineering Resource Center in San Jose, we have our engineering manager, Christian Maraglia, and our sales engineer, James Pedu. And that about sums it up. So we would like to thank everybody for taking the time to listen to our webinar. This material will soon be available via our website, www.fujipoly.com. Fujipoly would like to do a couple more webinars this year, so please be on the lookout for our announcements. We will momentarily begin our Q&A session. Okay, so we'll go ahead and begin answering some of your questions here. I see more of them are coming in, so we'll try to grab those as we move along. So let's see, one of the ones that I'm looking at here, can you dispense these types of putties? No. So the putties that we discussed, the PG25A, GRPM, PG80A, those are specifically in sheet form so they could be easily handled. Our dispensable product line consists of our SPG type materials, which are silicone gels, and those are dispensable. So these putties are in sheet form and they're intended for ease of handling manually. Another question, is the putty material already cured or needs to be cured after application? There is no post-curing of this putty type material. It comes in sheet form already as cross-linked as it's going to be, and there's no added process for the customer. Okay, another question, what is the shelf life on putty material? Our putty has a shelf life of 5 years from date of shipment. Another question we have here is, how is the material supplied? Okay, so the putty originates in sheets of about 300 by 200 millimeters in thick in area. Custom sheet size is available upon request. We could cut to just about any size or shape. You know, just to recap what I said before, squares and rectangles require no tooling because they're done on our super cutter as shown in the presentation. We also have a proto cutting machine, which would just require a PDF file, so we could produce a sample of a custom cut part without needing to purchase a tool, and we could also do our own die cutting for you as well. Let's see here. Okay. All right, another question on the UL flammability ratings of putty materials. So they're all rated B0 for flammability, and we have our UL yellow cards available on the database for these materials. Another question is, what is the operating temperature range? Recommended is negative 40 C to 150 C, and higher temperatures are okay for short durations. Another question is, what are the thermal conductivity values of the putties? The range would be from 2.8 watt per meter Kelvin up to 13 watts per meter Kelvin. And there's a question on silicone oil extraction test performed. So we do perform Belcore testing on all of our materials, which is available upon request. For further information, please send an email to info@fujipoly.com or contact one of us directly and we'll get you that data. Okay, and another question is, how do putty materials compare to the other Sarcon materials regarding silicone exuding or outgassing? So outgassing is actually very low. We test all of our materials to the NASA ASTM E595 test for outgassing, which measures total mass loss, condensable materials, and water vapor. It's well below the limits for all of those criteria. Can you comment on the adhesion of the material on metals such as aluminum, if any? Actually, the adhesion of the putties have great adhesion characteristics. And one of the questions that we also get, just to add on a little bit to that, is how reliable are the putties against heat shock and vibration? And part of the answer is the adhesion. That's what makes it resilient in rugged conditions over time. Our putty type gap fillers have a high inherent tack. So once it's placed in between its two intended substrates and compressed, then it really fills in and conforms to the surfaces and creates a surprisingly strong adhesive bond. So this bond allows it to perform through some vibration and cycles of thermal expansion and contraction. Now, we always obviously recommend thorough testing on the part of our customers to ultimately verify that the material performance over time is going to be, to your standards, but we're confident in the putty's ability to perform in most applications over long periods of time. Let's see, what other questions? I have a question on which new products are being developed. So in the short term, there are no new gap filler pads being introduced to our product line, but we do have some new dispensable products which will be released, and we're working on rolling these out. So that will consist of both non-curing form-in-place materials and two-part cure-in-place materials. So stay tuned to Fujipoly's website for announcements on new materials, hopefully soon to come. Another question, how does peak force of putty compare with similar property gap pad? Also, how does the relaxation force compare with gap pad? So the peak putty, generally the peak compression will be lower with the putties than it is for the general purpose gap pad. And again, that has to do with the way that the material is cross-linked. It has more plasticity than the standard gap pads, which have a little more elasticity to them. And then as far as relaxation goes, we also expect the putties over the long term to relax more, and for the same reason, due to the cross-linking and the way that the material is cured. Okay. I have a question about silicone-free gap putties. Unfortunately, at the moment, we don't have any sheet-type silicone-free putties, but as I mentioned a few minutes ago, we are working on a new line of dispensable form-in-place putty-type materials. So this will be a dispensable type putty, which will have non-silicone formulation. So again, stay tuned or reach out to us directly, and we'll try to get you some preliminary information on those products if you're interested. Trying to see if we got all the questions. Okay. When will you be doing your next webinar? So I believe we're scheduled for another Thermal Live, which is maybe late spring, if I'm not mistaken. So look out for Thermal Live, which will be in a couple of months. And then, so this is the first webinar hosted directly by Fujipoly using the WebEx application. So we definitely plan to do some more, maybe one more this year, once or twice a year at least. So stay tuned, and we'll be providing more information on our lineup of future webinars. Let me scroll up here a little bit. See if I missed any questions. All right, so when is a dispensable material better than a putty? When manufacturing target throughput is very high, then a more easily automated process, dispensing thermally conducted gel, might be more attractive. The other reason would be if, an even lower insertion force than what our putties can provide is desirable. That would be another reason. So, you already tried the putties because you can't take too much pressure. The only thing really, the only option to go to would be a dispensable type material, which has nearly zero insertion force. Okay, and I think we just about answered all the questions we can answer at the moment. Oh wait, here's a new one that just came in. After you apply the putty, what happens to them over time? In other words, can the parts be easily separated after some days, weeks, months of use? So typically the residual load, the static load, will not go to zero with these putties, especially if you're compressing it initially above 10 to 30% of its initial thickness. There will not be a zero static load, but on top of that, as I stated earlier, the adhesion property of the putties to their substrates is really what you're looking for to provide long-term reliability. The strength of that bond is, in the long term, what's going to keep the material performing as good as when you first install it. Okay, so I think that's the last of the questions for now. Again, if anybody would like any samples or any additional data, there might be one or two questions if you didn't hear the answer to your questions, we'll reach out to you directly, and we'll try to get those answered to you. And please feel free to request any samples or any additional data that you might need. Okay, and that about sums up our webinar. Thank you, everybody.
Ladies and gentlemen, that concludes today's event. You may now disconnect your lines, and have a great day.